All right, so in 3.5, we're going to talk about the kinetic molecular theory. And at the very end of this, I'll talk about 3.6 as well, because actually it's just a couple of more statements beyond this. But in 3.5, we're looking at KMT. And there's a couple of things that you should know for the exam or know about this particular topic, and that is the 5 assumptions. Those assumptions are the following. So there's 5 of them. And so 5 assumptions. And these are the assumptions that are essentially kept for gases that are behaving ideally. So these are ideal gases at play here. So the first assumption is going to be that gases are in constant motion. Okay. And that motion is linear motion. The second thing is that temperature, and I'll abbreviate that as temp, is going to affect kinetic energy. And specifically, it's proportional kinetic energy relationship with temperature. So what this is essentially referring to here is as the temperature goes up, this is going to be directly proportional to the kinetic energy. And that means that there will be a proportional increase to the kinetic energy of the gas. The third assumption of the kinetic molecular theory is going to be that the volume of the gas particles are negligible. And fourth one here is going to be that any collisions that happen to occur with gas particles, or I guess for that matter also with the containers of a container, or rather the walls of a container that the gas might find itself in, those interactions or those collisions are also negligible. So collisions are negligible. And then the last one here is that intermolecular forces, which we've already discussed in the previous units, the intermolecular forces are also negligible. Okay. The main reason that this is true, if we go down the line here, is that the kinetic energy of gases is just very high. So we know that that's going to lead to this constant motion. We know that the temperature is going to affect that kinetic energy. So that assumption there is very good. Now keep in mind that when we're dealing with these ideal gases, there's two particular temperatures that we're mainly worried about, or the temperature here for these ideal gases is going to be at high temperature. And so that's important. Now the other condition that needs to be addressed here, since we're on the topic, that means that these ideal gases are operating at low pressure. So that's an important thing there. So with respect to steps 3, 4, 5, or these 3 assumptions here, the reason we can consider them to be negligible lies in the fact that, one, gases have a lot of space between individual particles. But if you take that gas as a whole, the gas as a whole does occupy space, but the individual particle itself is actually very, very small. And so the volume that it occupies is extremely small and virtually it could be essentially as negligible in terms of our consideration. Now the collisions are negligible largely because the kinetic energy of one molecule, when it collides with another molecule, is essentially going to transfer that energy to the other molecule and vice versa. So there is definitely no or very, very little loss of kinetic energy here for the gases. Now the intermolecular forces are negligible because the gases are at constant motion, which means that their kinetic energy is high, and therefore any interaction that would take place is not going to be any significant factor in terms of keeping those gases together. So as long as those gases are in constant motion, as long as the temperature is at a reasonable temperature above the threshold, then those gases are going to remain in motion, and any kinetic energy, or excuse me, any intermolecular forces that may occur or potentially occur are going to be so small to insignificant that we really don't consider them at all. Now, these here are related to ideal gases. Now, keep in mind when I talk about this here at the very end, when we deviate from these high temperature, low pressure conditions, and that means each of these 5 different assumptions can no longer be considered, and those are the conditions that you're going to find for real gases. Now, so let's make some space here. Let's kind of move these things over here, move these over to the side. And the one thing that I do want to make sure that we address here in this area is this concept or this idea of how do you compare gases from one area to another, or how do you compare between the gases in terms of kinetic energy, for example? Well, for that, we have to use a distribution model, and that model is essentially the Maxwell-Boltzmann distribution. We represented that before in class like this. The temperature was on the x-axis, and the number of particles was represented on the y-axis. Now, keep in mind that when we say temperature here, this is at a single temperature value. There is no difference from left to right. And so what we're asking oftentimes, or what you may be asked to do, is to represent a gas in terms of its distribution relative to the kinetic energy contained by those gases or held by those gases. One thing you should always remember here is that the average kinetic energy of the gases at a temperature, okay, remember this is at a distinct temperature, so let me put that here, distinct, is the same. Okay, but when you're looking at one particular gas, those particles in the gas are not all going to be traveling at the same kinetic energy, largely because the relationship to the source of energy that is applying the temperature, and by extension the change in the kinetic energy, it's not going to be applying to all of them. So whenever we refer to gases, we tend to refer to it as the average kinetic energy. So a normal distribution here for a gas essentially is going to be roughly like this. And so not to get too much into it, but the center point of this here is representative of the average, which is going to be here, the x over the with a bar on top is equal to the average. And this is going to be the kinetic energy that we're talking about. So what we can see is that some particles will be below the kinetic energy or the average, and then some particles will be above. So what I've drawn here is a very generic distribution. It assumes, at least the way I've drawn it, it assumes a normal curve distribution. But in reality here, you may be asked to compare the kinetic energy distribution for one gas versus another. So if this is the baseline here, the question that's going to be asked is, can you redraw the distribution based on a variety of different conditions, either that being colder or hotter than the current state of temperature, or whether you have heavier or lighter particles. So the main thing to remember here is if you have lighter particles, so obviously lighter means that you're going to be able to have a higher kinetic energy, so there's going to be an increase to kinetic energy. So if we're talking about a graph here, we're going to see this represented relative to what's already there. This is going to be a shift to the left, or rather to the right, because essentially the kinetic energy here is going to be a little bit higher. So you could also see that the baseline here, even though we're representing t, we can also use this as a proportional increase, so that if we do this, include this as a linear progression, we notice that at this point here, this temperature, the average kinetic energy would be here, but lower kinetic energies would be represented further to the left, and higher kinetic energies would be further to the right. So here, lighter particles would move faster, so they would have a higher kinetic energy, so we would expect to see a distribution this way. Since the area underneath the curve is going to stay the same, what we would see then here, if I represent that as a yellow, you'll see that the distribution would actually shift and it'll broaden off. But notice here now, the average distribution is actually over here at the second point here. And so the other condition that you could expect to see here is what is if you have a heavier molecule. So essentially heavier molecules are going to be moving a lot slower than the lighter molecules. So you would see here a reduction in the kinetic energy. And so this should actually be represented as a shift to the left. Okay, and so just keep that in mind. Now, remember, since temperature is proportional to kinetic energy, here what you can make in terms of distinctions here is if the temperature goes up, so obviously that is going to lead to an increase in kinetic energy, which should lead therefore to a shift to the right. I'll represent that with an R circled. And then if you have temperature decreasing, then you see that proportionally related to a decrease in kinetic energy, which should cause a shift in the distribution to the left. So these are some items that you want to make sure that you keep in mind as you continue your review of individual problems. But generally, these are the concepts, and this graph at the very top, remember, this is the Maxwell-Boltzmann distribution. So it's a matter of distributing the gas particles overall when you consider them or when you try to compare them from one gas sample to another gas sample. So the next item that we want to talk about here is the what happens here with when gases. Previously, I had referred to them as gases. When you put them together in a container, we want to ask ourselves, well, what happens if I try to let the gases escape? What will happen then? And so let's kind of move these things around. I'm going to kind of make some space here overall for us, just to make sure I can accommodate everything on the screen here. So we'll put everything down there. And now we want to take the condition, if let's say that you have gas 1 versus gas 2. Now, we know that each gas is going to have its own kinetic energy, say kinetic energy 1, and then gas over here is going to have kinetic energy 2. We know that the kinetic energy is equal to 1/2 mv squared. However, when we talk about comparing gases, particularly if we have them inside a container, and let's say that the gas 1 is a blue dot represented there, and let's say that the gas 2 is a green dot. So if I have these gases inside a container, and I'm representing the green, and I've got the blue, they're all mixed in here, we could, if this was section 3.4, we would be talking about the average pressure or the total pressure of the system. Here, we're not concerned with that. For this section, what we're concerned about here is what happens if I were to come in here and essentially poke this section, and I create a pinhole. Okay, and now there's an escape. Some of these gases now are escaping, and so we're going to see here gas 1's going to come out, or gas 2, and the question typically is which one is going to escape first. So the main thing that you want to remember here, or key point here, is that lighter gases travel faster. Another way of saying the same thing is that these lighter gases are going to have higher kinetic energy. Now, in contrast, on the opposite side of the things, if you're a heavier gas here, then that's essentially going to mean that you're going to travel slower, and by extension, that means that you're going to have a lower kinetic energy overall. Now that's important because when we're trying to talk about escaping from a container with a pinhole, this process, or this section here, is known as effusion. And the effusion equation, I'll go ahead and write this down, so I'm going to refer to effusion down here. And the effusion equation is essentially the following. 1 over the square root of the mass of the gas in question. Now, you could always use Graham's law, which I'll show here in a second, but if you use this equation here and then just compare the two, then you should, or 3 or 4, however many gases you have, you should be able to get the answer as well. Now, the other equation is Graham's law. And so let's write that down at the bottom. And this is very useful. It's essentially effusion, but you're combining two effusion values together for two different gases. Here, this particular version of the gas law, it combines them already into one. So here we're going to compare two separate gases. So we're going to look at M1 over M2. And this is going to be equal to the square root of the second mass over the first mass. And so here the M1 can be representative of the kinetic energy as well, or the rate of effusion of the first versus the second. But this equation here will be very useful for us as we compare. So we did a lot of sample problems in class, but essentially here the lighter gas is always going to move forward. So I'll do a quick little sample here. Let me just move some stuff out of the way and we'll go forward from there. Okay, so let's see, let's move some of this stuff out of the way. Just create a little bit of space, move it all over there. And so if I have a sample problem here, let's say that I have a couple of gases, and I'm just going to make some stuff up here. We've used quite a bit of them already in class. But what if I have something like HCl versus, I don't know, well, actually, let's do another one. How about CH4? let's say I consider these here. The main thing you want to do in terms of trying to figure out which one is going to escape first from a container is you first figure out the molar mass. So the molar mass of HCl gas essentially here would be, see, 1 for the hydrogen plus 35.453 for the chlorine. So if we add these together, that would be 36.453. Now if we take the mass here, or the molar mass of CH4, I'm just going to do this down here. The carbon is going to have a mass of 12, and then the hydrogens are a mass of 1. There's 4 of them overall, so that will give me a total of 16. This is going to be grams per mole here, and then the same units on the other one over there. So since we see that the HCl has a higher mass than the CH4, 16 is the grams per mole, the molar mass there, we would say that since CH4 is lighter, then we would say that it would actually effuse faster than the HCl. So that would be a conclusion that we can actually reach here. And so therefore since the CH4 is lighter than HCl by molar mass, and you can write down the numbers in your explanation if it's an FRQ. So since it's lighter, therefore CH4 would effuse faster than HCl out of a container. Now, if the problem is asking you to compare how much faster, then definitely you want to use Graham's law here or the effusion equation and just compare. So if that's the case, you definitely just want to go ahead and use those equations and solve it out. So if I'm trying to do the solving here, let's go ahead and do that. I'm going to use yellow. So I've already got the molar mass of HCl and CH4. So what I'll do here, since I've only got 2 gases, I can use Graham's law. But if you had 3, then you might want to use the effusion equation for each individual gas. And so I'll use that version, but you could use Graham's law in this particular case. But let me just use the effusion equation, and you're going to see it's the same thing at the very end. So since I'm referring to a comparison between 2 gases, I want to take the lighter gas. In this case, it's CH4. Notice the mass is 16 grams per mole versus 36. So the relationship that I'm going to do here is I'm going to take the relationship of CH4 relative to HCl. And so that means here that this essentially, I'm going to take the mass of the first gas versus the mass of the second. And this is going to be proportional here. If I do that, the relationship for the first gas is essentially going to be 1 over the square root of the first gas. And for the second one, it'll be 1 over the square root of the mass of the second. So if you think about this very carefully, what you really have got here is Graham's law. But the numbers here, we kind of do the numbers. For the CH4, we knew that the numbers there were 16 grams per mole. So we would say 1 over the square root of 16 over the second gas, and that would be 1 over the square root of 36.453. So down here in the numerator here, we're going to get 0.25. In the denominator here, we're going to get the following number. That's going to be 0.165. And if you do the math all the way through here, you can see that the ratio, the top number is a lot higher. So you're going to have a number here that's greater than 1. But just to compare here, notice here the 0.25 is significantly higher than 0.16. So if you do the number here and actually do that math out, you're going to get 0.25. Divide that by 0.165. The value is 1.515. And so that means that this value here, this 1.515, is the number of times that the faster gas, in this case CH4, effuses above the other gas, which is the CHCl4. So CH4 will effuse 1.515 times faster than the CH4 in comparison. So that's an important thing to do there. You should be able to calculate that out. So take a look at some of the questions that we've done in class as you go through that. and just be aware of how to do that. Now, I did say that I was going to address 3.6 here in this video, and I'm going to go ahead and do that now. And all that means here is that when we start looking at these deviations, we're going to see that the deviations from ideal, in other words, we have to go back to the overall original statements here, the kinetic molecular theory, are at the very beginning. So let me zoom in on those and just stay the principle that applies when you deviate from ideal conditions. So let's zoom in on that. So essentially this right here. And so what I'm saying is when you deviate from high temperatures and low pressures, what's going to happen here is that we can no longer make these assumptions that are true for the ideal gas law conditions or for gases at ideal conditions. So whenever we have real gases, that means that the temperature might be lower. And a lot of the real gases, what we're referring to there is temperature at real conditions, which is essentially ambient. So I'll kind of make the note over here that when we're dealing with real gases, here we are essentially dealing with lower temps are involved, and typically that could also be maybe higher temperature or lower pressures. But the idea here is specifically related to the key variable is going to be the low temp, lower than ideal. And so with that regard, what does that mean? That means that the kinetic energy then, since it is proportional to the temperature, then here, although this is still true, the temperature is going to bring down the kinetic energy. So that's going to mean that the kinetic energy will see a decrease, which means now that any interactions that we previously considered to be negligible in the intermolecular forces, we now see that those interactions are going to be increased. So here the intermolecular forces now can increase or a little bit higher. And also that means that things like collisions are also going to not be negligible anymore. And so without kind of going too much into this, it just means that if you are considering a real gas, then that means that the conditions that were available for ideal are no longer applicable, and which means that all of these assumptions can no longer be made. And so that you have to take into account the intermolecular forces now. They must be considered. And so because of that, you need to make sure that you make some significant gains here in this regard to consider not only the intermolecular forces for real gases, but you also have to make sure that you consider any polarity in that mix, because as the intermolecular force goes up, and so we'll finish it up here, as intermolecular forces go up, this means then the deviation is going to increase. So if we're referring to how far a gas will deviate from ideal conditions, it'll deviate quite a bit if the intermolecular forces are at play, because that means that the gas is slower and it actually could be closer to going into the liquid phase, which is a problem if you're considering gases that are supposed to be operating presumably at ideal conditions. So those are the final two sections for 3536. In the next video, I'll briefly discuss 3.12 that deals with the photoelectric effect.